I'm Kurt. Welcome to Comp Sci 5. Today's topic, trees, baby. Everybody loves them trees. So, today we're going to do trees, and trees are a really cool data structure. So let's just rehash the data structures we've learned so far. So we've learned about the array, which is good for accessing an element by index to grabbing it instantly. We learned about a linked list, which is good for adding elements to it. You can choose to implement a linked list with a stack or a queue. Both have constant time operations for inserting and deleting. Remember, stacks, you push on top and pop off the top, whereas queues, you enqueue in the back and you dequeue from the front. Now, these data structures are all linear. They're all lines. And what the limitation to that is if you're searching for an element in them, well, that's going to be big O of the length of the list itself. So we need something to represent a different type of data, and not all data is linear type. Data could be hierarchical, in which case, boom, we have a tree to describe that. Now, what's important to note is that all these data structures, they have a common root, if you will, with this here node. Remember how awesome and cool nodes are? Because a node can take in any kind of data item it wants, and remember, it has references to the next node, but who says that it only has to have one reference, right? A node could have as many references as you want. You only need to pay 4 bytes of data for that overhead of storing a pointer, which is just an address in the computer's memory pointing to the other node, the other box in the computer's memory, right? So up here, I've drawn a beautiful tree for you, and how we're going to do it is just introduce some vocab. This is just going to be an intro on trees. Later we'll get into how cool trees really are and how you can leverage them to meet your computer science needs. So we'll start off with the root, and the root is always at the top of the tree. So trees like are upside down if you think about them in the computer science world. This is how we draw them because, well, we're a little bit odd. So here's the root of the tree, and a child is right here. So 2 is the child of 1 because this is below the root, right? Likewise, 1 is the parent. Here's all the vocab right here. 1 is the parent of 2, okay? Now, if 2 nodes share the same parent, as in the case with 2 and 3 share a parent of 1, then 2 and 3 are siblings. It's kind of like how you and your brother had the same parents, therefore you're siblings, right? So now we're going to talk about what if a node doesn't have a child, which in the case of these nodes right here, okay? If a node doesn't have a child, it's called a leaf, right? It's literally called a leaf. Anyway, so leaves are also called exterior nodes because they're on the exterior of the tree. If you're not an exterior node, you are an interior node. So for this tree, we have node 8 is a leaf, we have 13 is a leaf, 5 is a leaf, 10 is a leaf, 11 is a leaf. All the non-leaves, all the non-exterior nodes are interior nodes. Now, an ancestor is, like you would guess it, comes up top. It would be like a parent is an ancestor of a child, right? Like 1 is an ancestor of 2, but 1 is also an ancestor of 4, 1 is also an ancestor of 9, 1 is an ancestor of all the nodes in the tree because it's the root of the tree, it's the start of the tree. A descendant would be like a child, right? So 11 is a descendant of 7, 11 is a descendant of 3, 11 is a descendant of 1. Great. Now we're going to talk about a couple of properties. So the depth of a particular node is the amount of links, which are these arrows, from that node to the root, right? Depth, think about it, is you're burying the node from the root. So the depth of root 3 would be 1 because there's one link between the root node and the node. The depth of 5 would be 2 because there's 2 links. The depth of 13 would be 1, 2, 3, 4, 5. Great. Height, on the other hand, is the distance from the node that you're talking about to the furthest leaf, the longest path to the furthest exterior node. So the height of 3 would be 2 because 1, 2 is the furthest. All right. Well, how about we'll talk about 2? The height of 2 is not 2 to 8, which is a leaf. The height of node 2 is 1, 2, 3, 4 because 4 is a longer path than 2. Therefore, 4 would be the height of node 2. Awesome. So now that we got a handle on trees, trees are great because when you're searching for a node, instead of searching through a whole list in a linear style, we can do something called a binary search tree, which we'll get into next time, where the properties of it would be the nodes to the left are less than the root and the node to the right child is greater than. So in other words, you wouldn't have to search for it in big O of n, it would actually scale to the natural log of the amount of splits there are. In the binary case, it's 2. Thank you for being with us today. That was Comp Sci in 5, and next time we're going to get into pre-order, in-order, and post-order traversals, as well as some other properties of trees. Thank you for watching.